So far we've built the oscillator, video basics, borders, ball counters, ball motion controls, bricks, ball and play counter, and serve logic on sheet 1, the paddle logic on sheet 2, the start game controls and operational latch on sheet 3, and the flip screen circuit on sheet 4. Today we'll build the last remaining visual element, the on-screen display from sheet 2. Once again, we're using the RevFX schematics because the RevF schematics in the manual don't exactly match the RevF boards. See Part 2 or the differences document in GitHub for details. In Part 1, we discussed some chip challenges, and one of the topics was replacing the 9000 series chips with 7400 series. Here we're replacing 9312s with 74151s. And this is one instance where the parts are logically equivalent but not pin compatible. 9312s are hard to find and quite pricey. If you need to replace 9312s, I created this little converter board that simply remaps the pins. Just solder headers to the 9312 site and add a socket for the 74151. I dropped a zip file into GitHub with the manufacturing data that you can throw at your favorite fab. If I load this onto JLC PCB, have them panelize it, and use cheap shipping, I'll get 45 individual boards in less than 2 weeks for about $10. Probably less than it would cost me to send you some. We'll need a bunch of those 74151 multiplexers in Nancy 5, Mary 5, Love 5, King 5, Henry 5, and Jack 4, a new 7-segment decoder in Jack 5, a new triple 3-input NOR gate in Mary 8, and a new 555 timer in Baker 2. We'll also be using a bunch of gates from chips we already installed, and we'll need a few passives. We can break the display logic into 3 parts: the digit value funnel, the segment decoder, and the final score output. There are 8 on-screen digits. These multiplexers pick which digit position is fed to the segment decoder based on the selector inputs driven by vertical signals. Each multiplexer handles a single bit for all values, so Nancy 5 handles the low order bits, and King 5 handles the high. Walking down the inputs, you can see that player 2's score is fed into inputs 0, 1, and 2. The ball and play number is fed into input 3. Player 1's score is fed into inputs 4, 5, and 6. And the player up number is fed into inputs 7. Mapping this out, input 0 is gated through when 128 Victor, 64 Victor, and 16 Victor are low, so it sits in this vertical lane, but it also sits here. Digit 1 sits here and here, and the rest of the digits also appear in 2 places. We need to take a peek ahead to the output section to resolve this. We can see that the output from the segment decoder passes through this gate, so the other inputs must be high to pass the segment data. The trick here is that 32 Victor and 64 Victor must be different for this input to be high, which happens here and here. So we can eliminate these other positions and our final digits will sit in these vertical lanes. For the horizontal space, 32 Henry must be on to get segment data from the decoder. That happens in these 4 areas, and we need to look into the output section again to resolve this. For segment data to flow through this gate, this score enable line must be high, so these inputs must all be low. The not top signal drops when 64 Henry and 128 Henry are off, limiting the horizontal space to just this one area. The last horizontal delineation is decided by this gate when PLNR and 16 Henry are different. PLNR is on when 32 Victor and not 16 Victor are off, and this happens for vertical lanes 3 and 7. I guess PLNR is player number in position 7, but we can see it also rises during the ball and play number in position 3. Anyway, when PLNR is on and 16 Henry is off, digits 3 and 7 appear here, and when PLNR is off and 16 Henry is on, the remaining score digits appear here. The next item in the output section is the score flash logic. This line must be low to turn on score enable, and that happens when any of these inputs is high. It's easier to think of this backwards in that pin 12 is always low or always enabled except when all of these inputs go low. We already know that PLNR is high for digits 3 and 7, so that blocks those two digits from potentially flashing. We also see that this output goes low when not player 2 and 128 Victor are the same, so when player 1 is up, digits 4, 5, and 6 can potentially flash, and when player 2 is up, digits 0, 1, and 2 can potentially flash. Now that we bring pins 2 and 13 low during specific digits, we need to bring not SFL down to blank out those positions. This 555 is configured as an oscillator running at 4 Hz with a 50% duty cycle. When in attract mode, the output is off and not SFL is high, disabling any flashing. While playing, not SFL toggles at that 4 Hz rate, causing the player up score digits to flash. Finally, the score enable and score segment data lines are merged and inverted in this gate, re-inverted by the spare flip latch and placed on the video bus. This is a strange configuration for a flip latch, but if you look at the internals, it's just a bunch of gates, and if you tie down the other inputs, this NAND gate simply becomes an inverter for the set input. We'll get to the segment decoders in a bit, but we now have enough logic built to show where the digits sit in the visual space. Let's just shove 32 Henry into here for now and turn this on. Big fat blocks where the digits will sit, and the blocks for player 1's score flash when we start a game. And player 2's blocks flash when player 2 is up. These blocks are a little fat and get narrowed down by the enable lines on the segment decoders. You can see that the vertical generator is enabled except when both 4 Victor and 8 Victor are on, so the boxes will get smaller like this. The horizontal generator is enabled except when 2 Henry, 4 Henry, and 8 Henry are on, so the boxes will get smaller like this. We can quickly shove these two enable lines and not 32 Henry into a triple 3-input NOR gate to see our trimmed boxes. That looks a lot better. So let's go finish the segment decoder section. Digit values from the funnel are decoded into 7 display segments by the 7448 and Jack 5. You've probably used 7447s in the past to drive common anode LED displays. Both the 47 and 48 take in a decimal value and emit standard digit segments A through G. Here the segments are gated by these two multiplexers. The top multiplexer handles the horizontal segments, while the bottom one handles the vertical segments, as they clearly point out. For the top one, segments are gated by 8 Henry, 4 Henry, and 2 Henry, so segments A, G, and C appear in these slots. The vertical segments are gated by both horizontal and vertical signals. Segments B and C are gated when 8 Victor and 4 Victor are off, and this is narrowed to just segment B when 8 Henry is off and to segment C when 8 Henry is on. Segments F and E are gated when 8 Victor is high and 4 Victor is low, and this is narrowed to just segment F when 8 Henry is off and to segment E when 8 Henry is on. The segments are overlapped but still create reasonable digits. Horizontal and vertical segment data is then merged in this NAND gate, and I just now noticed that this is missing the output dot. actually would be better represented as a negative input OR, since we want the output to go high when either input goes low. But we'll just add the dot to the schematic. I'm going to temporarily jumper the funnel values to their digit positions 0 through 7. And let's turn this on. Nice. Properly displays those values. We're going to do the scoring in the next video, but we can at least wire in the player up and ball and play values. This logic converts the 0-based binary values to 1-based values for the display. The player 2 line is 0 for player 1 and 1 for player 2. And the conversion truth table is simple. We tie down the first 2 bits, use player 2 for B, and invert player 2 for A. Adding a 1 to the ball number is a tiny bit more complex. Again, we tie down the unused bit and invert the low order bit. If we flatten this out, the rest looks pretty familiar. Here we have a half adder with sum and carry, and another half of a half adder with just the sum. I guess it's a half adder and a half, or 1.5 half adders. Your choice. Anyway, let's turn this on and take a look. I hardwired the player scores to all 1s and 2s for now. Reset. Start a 2-player game. Shows player 1 is up. Then we move to player 2. Next, we move back to player 1 and the next ball, and so on. Let's start a 1-player game. The ball and play counter increments and displays properly. Let's do a quick test for flip screen. I just need the jumper for cocktail model and start a 2-player game. Score shows up in the proper place and works nominally. I actually had a bunch of issues getting the 7448s to work properly. The only way I could get them to work was by specifically pulling up the lamp test pin, tying down the ripple blanking input, and hooking 32 Henry to the blanking input. Tying down the ripple blanking input is normally used to suppress 0 values, so this is pretty strange. I also noticed another anomaly. All of the datasheets for these show that input values past 9 emit some funky segments, but you can see on this test setup that values past 9 emit blanks. Another issue is that the chips don't turn off quickly enough and bleed here. I thought I bought these from DigiKey, but I took a look and these came from eBay. 7448s are no longer available from major supply houses, so I went back to the trough and ordered a few different parts to test. The funky chip is on top, supposedly a TI SN74LS48N. Then I've got 2 plain old TTLs from NTE and Signetics, and also this LS248 from Motorola. The 248 is the same as the 48, except they add tails to the 6s and 9s, if you're into that. All of these 3 other chips seem to work properly. They all show the weird characters after 9, and all 3 will blank out zeros if I pull down pin 5. They also all work in the breadboard, wired per the original design. They also turn off properly and don't leak over the top segment. My original set was most likely fake. Drove me absolutely nuts. 74LS47s are a lot more common, and you can still get them from major supply houses. I'm almost tempted to use 47s here and then route the positive outputs from the segment multiplexers. I'll just leave that 248 in there for now and let's move on. Chuck today's work into our retro schematic. Add all the parts. Rename everything. Add nets. And wire it together. I thought that game state video was tough, but this one had a ton of nets to wire up. As we move further along, she's getting more jammed up. And I'm not trying to make this pretty, I'm trying to make it done. I'm surprised she's still working okay. I'm just not going to say that out loud. Pain in the ass. In the next video, we'll do the scoring. Thanks for watching.